Hello, dear students. Today we will start a new example about the pressure vessel. Its inner diameter is 80 millimeter, outer diameter is 100 millimeter with depth of 160 millimeter, or height also we can consider it. The Young's modulus 200,000, the Poisson ratio 0.3, density 7,800. Times 10 to the power of 9 minus 9 kilogram per millimeter square. To do so, we'll start with ANSYS APDR, define the properties, structural preferences, then the preprocessor, the element types. For the first time today we'll use another solid model, which is 4-node 285, TET 4-node 285. This model has no options, so there is no options, no thickness actually, no real constant. So material properties, with material models we go to structural, linear, elastic, and isotropic. Again, same. According to that properties is 200,000, so 200,000, so 2e to the power of 5, Poisson ratio 0.3. Okay, for first time we use density today 7,800 to the power of minus 9. Okay, so that's all about the properties already done. Then we'll go to modeling, create using volumes this time, cylinder, hollow cylinder, so XY let it empty as a 0. R1 will be 40. Need to check, it is 80 and 100, so 40, 50, the radius, 40 R1, 50 R2, and the depth 160, or the height of that pressure vessel. Okay, so we got it here, you can see 3-dimension. Now let we go to meshing, mesh tools. We will use set global as a 3-dimension. Let we use 5 here, because less than 5 it will take time, and also the speed of this PC may be not enough to get that numbers of elements. Okay, so now just select. Okay, we got it, the mesh. To see how many elements we have here, go to list elements and just have a look here. You will find it is 23,300 plus, so it's huge number of elements. Now let's go to solution, to analyze types, always static, just to be sure, and define loads, apply structural and pressure on area. To select area here, it's a little bit difficult. You can see it's not simple, so we can see the area number here is number 2, then this one number 6, which we are looking for. Another click, it's not our area, not required area. This is the required area, the upper. So the internal surface of the pressure vessel we are looking for, so just cancel, go again to select the area, so you can write here 5,6, and okay, so we can select it. The pressure is 100,000, so 1e to the power of 5. Okay, so we got it here, as you can see. For the boundary condition, we want to fix this pressure vessel in one line, the tangential line along the pressure vessel. So to do so, we will go to displacement, apply displacement on nodes, and let we go to side view for this pressure vessel and use box. Then we want to select this is 20. You can see here the count is 20. I will show you. Okay, in Y direction, 0 displacement, and then okay. Now let me show you. You can see here we fixed that this pressure vessel from the line along the bottom tangential line, which has 20 nodes. Now just go to solution, solve, current line steps. Okay, it will take a little bit time, not so long, but that's all because of the number of elements. Now the solution is done. Close this one, and go to the general post-processing to get the final results. So plot results, deformed shape, deformed and indeformed, just to see, just have a look. You see the solid area, the blue area, and the mesh. It's so clear. The deflection, the deformation, it is 281 millimeter. It's big, a little bit. From contour plot, also nodal solution, you can check the degree of freedom solution in X direction. You can see here from that side. You see here in X direction or Y direction also. Y direction along. You can see it's along the pressure vessel. The same way in Z direction. Force stress also in X direction. This is in X direction. You can see here from both sides, the side from that side, and in Y direction, in another side from here and here. You can see also from both sides. While in Z direction, almost you cannot see here. Better to use von Mises. From stress, just go down. Von Mises stress. So the averages here you can see along the pressure vessel. Now let we use actually to get the what we call it the circumference stress on circumferences here in the middle of the diameter, the inside diameter, inner diameter, outside diameter. We want to see the stress distribution along, or stress concentration along the midpoint of this thickness of the pressure vessel. So to do so, let we go to plot elements, get side view like this, better fit. Okay, so now we will use also new path operations. Define path on working plane, circular path. Okay, now we have 40 and 100, 40 and 50, so in between is 45. Okay, you can call it path or whatever name you can use here. So you can see here this line goes a little bit dark. So now we will study the stresses. It's very important to study the stress concentration or distribution along this line in the midpoint of the pressure vessel wall or the thickness. Now we can use map onto path to select. This is the deformation solution. So in X direction apply, in Y direction apply, in Z direction apply. Also we can go to stresses, select stresses in X direction, apply, Y direction, apply, Z direction, apply. Shear also in XY plane, YZ and XZ. Okay. Also we can select the first principle stresses. Second, it is very important to get the results in a graph, so we need to select it from this menu here. Principal stress 3, and von Mises also we can select it here. Von Mises. Okay, last one. Now let's go to plot path items on a graph. From here you can select whatever, for example, deformation X direction. Say okay, you can get the exact distribution along the thickness of the pressure vessel. Where you can see the X, Y, Z deformation all together. You can see, and as regular actually in X direction the maximum values, then Y values and minimum in Z direction. Deselect the deformation and select the stresses in X direction, Y direction, Z direction. So you can see here almost same as X and Y, the stress values, while in Z direction it is in minus. Minus stress means compression, not tension. You can see also deselect this 3 and select the shear stress. You can see also in XY plane the maximum shear stress. Deselect the shear and go to principal stress S1, S2, S3. As you can see in S1 plane, which belongs to X directions, the highest value 40 Newton per millimeter square, and the minimum in Z direction, and then Y direction also less, and it's both in minus, means both compression while is tensile here, tensions here in S1 plane. Another thing you can see here, von Mises also we can see. Let we see the von Mises, the average stresses, as you can see here, how the stress concentration or concentrated along the pressure vessel thickness from inner to outer wall. Now let we try to use the plot control style graphs, modify axis. So you can modify the axis. This is X axis, we can call it circumference in millimeter, for example. The Y axis is stresses in Newton per millimeter square. Okay, say okay, and replot. So stresses, as you can see here, stresses in Newton per millimeter square, circumferences millimeter. Also you can change the scale if you want, the scale of the graph, modify axis. From here you can see X minimum, X maximum, specified X range. Instead of auto calculated, you can use the specified range and use the range which we are looking for, which is better for you to get the exact numbers, the accurate numbers of the stresses or the millimeter, the distances, circumferences. Y minimum, Y maximum here also you can identify from this page. That's all for the class of today. Hope it is clear for you, and thank you very much. See you in the next lecture or class. Thank you very much.